We have already encountered linked lists in conjunction with implementing stacks, queues, and collections. Our final use will be to implement the most general data type, a list that allows insertions and removals at specific positions. We begin with some general observations about the implementation that uses a linked list. As we have already noted in conjunction with their use previously, either singly or doubly linked lists can be used. But there is a trade-off. Double linking offers some benefits. Foremost, the ability to traverse either forward or backward. But that capability comes at a cost, which is that it increases the complexity of the code because whenever a node is inserted or removed, more links require modification. Unlike an array list, a linked list does not require shifting elements when an insertion or removal is performed, so both operations can be done in constant time. However, finding either the element or its position, which must typically be done before an insertion or removal takes place, requires searching the list. A linked list search must be done linearly, and that operation is O of n. Like all data structures, linked list operations can be implemented using iteration or recursion. Because a linked list is a recursive data structure, using recursion has some advantages in certain cases. In the unsorted implementation, all the operations rely on locating the position. In this case, we elected to use iteration. For the sorted implementation, using recursion avoids the need to maintain a two-node window, as was needed with the sorted array implementation we considered previously. There's only one method in the unsorted linked list implementation that we will examine. It is the method findElement that is called by the four methods that add, remove, get, or set an element at a specified position. This method is supplied the position whose element is to be located, and it returns a reference to the node at that position. The local variable count is initialized to 0 and will be used to determine when the position has been reached. The reference node will refer to each node as the list traverses. Unlike a loop that searches all elements of a linked list, this loop stops on the last node, which is the node that has a next reference that is null. When index and count match, the node whose position is index has been reached, and a reference to that node is returned. Otherwise, count is incremented, and the node reference is advanced. This return is executed when the index requested is the last node in the list. This method has an important precondition, which is that head is not null. The methods that call this one must handle the case when head is null separately. In addition, it assumes that the index supplied is always within the bounds of the list. That check is also the responsibility of the caller. We have provided a version of an unsorted linked list that uses iteration for each of its operations. You may want to return to the application that tests the unsorted array list and replace the array list with the linked list, and repeat the test scenario to confirm its correctness. As we did with array lists, we consider linked lists that are both unsorted and sorted. However, the Java collection framework provides only the former. Because we have already discussed the unsorted version, let's summarize the efficiency of each of its operations. Adding or removing at either end does not involve any searching, so both can be done in constant time. Adding or removing at a position in the middle of a list involves calling the method findElement that we just discussed. It involves a linear search, so it requires linear O of n time. Removing a specific element requires calling the indexOf method to verify that it is in the list and locate its position. Index of involves a linear search, so this one is also linear. Getting and setting an element both require calling find element, so they are both linear. And as previously mentioned, index of involves a linear search, so it too is linear. Let's compare the linked list implementation with the array list with regard to the efficiency of its operations, beginning with its advantage. The main advantage is that inserting at the head of the list is more efficient, since it is constant compared to the array list whose corresponding operation is linear. Next, the disadvantage. The primary disadvantage is that the get and set operations are less efficient. Now we consider the implementation of a linked list that is maintained in sorted order. We saw that an iterative implementation of a sorted, singly linked list requires using a two-node window during traversal. We will see next how recursion simplifies the insert and remove operations by alleviating the need for maintaining this two-node window. It highlights why recursion can simplify handling a recursive data structure like a linked list. We begin with the method that inserts an element. The add method that performs the insertion is initially passed the head as the node parameter. In this illustration, we will assume that 10 is passed in as the element to insert. The first check is to determine whether we have found the insertion point. That will occur when either we reach the end of the list or we find a value greater than the one we wish to insert. At this point, 5 is less than the value we wish to insert, so we have not found the insertion point yet. Because that condition is false, the else statement will be executed. Understanding what happens on this assignment is key to understanding how recursion simplifies this operation. On the right side of this assignment is the recursive call, which advances the node. The actual assignment will not occur until the method returns from this recursive call. On the second activation of this method, node has been advanced to refer to the node that contains 12. This time this condition will be true because 12 is greater than 10. So a new node will be allocated. The element 10 will be copied into the data portion of that node, and its next reference will point to the node containing 12. It looks as though the list has been broken, and there will be no way to get back to the previous node to connect it to this one. With the iterative implementation, that was indeed the case, which was why we always needed the previous current pair of references. But we have not lost the reference to the previous node. We will return a reference to the node that contains 12 to the previous activation. Notice that we return to the point after the recursive call. In the previous activation, node is still pointing to the node that contains 5. So we can connect its next reference to now point to the node that was returned, which is the node containing 10. We have shown this insertion in the case that it occurs after the first node. Had it occurred much further into the list, we would not only have a reference to the previous node on the compiler's runtime stack, but all the previous nodes. The preceding assignment would have to be performed for all those nodes, but except when the insertion occurs, it would just assign the same reference that was already there, because what is being returned now is a reference to the existing node. Now let's see how recursion can simplify the method that removes an element. What is supplied initially is a reference to the head and the element to remove. For this illustration, let's assume the element that we want to remove is a 10. If we reach the end of the list, or a node that contains a value greater than the one we are looking to remove, it means that element is not in the list. So we terminate the removal by throwing an exception. This exception is only used internally within the class, so we elected to use a predefined Java exception whose name is sufficiently descriptive. Next, we check whether the current node contains the element that is supposed to be removed. Initially, it doesn't match, so the else statement will be executed. This assignment contains the recursive call on the right side. So that call, which advances to the next node, must complete before the assignment can be made. On this activation, the parameter node now refers to the node containing 10. As before, the condition indicating it is not in the list is false. But now the current node contains the element that is to be removed. So what will be returned is node.next, the node after the one that contains the value 10, the one we want to remove. In other words, what is returned is a reference to the node that contains the 12. Now the assignment is performed. We have returned to the activation where node points to the node containing 5, and we assign that node's next pointer to what was returned, a reference to the node containing 12. Automatic garbage collection now deallocates the node that contained 10. As with the add method, we now just return a reference to the current node. So as the recursion backs out, all the assignments will not change any next reference. Recall that when using iteration, inserting or removing at the head is always required a special case. That special case is no longer needed because the initial call that started the recursion will reassign the head reference to the reference returned to it. That assignment will only change the head reference when an insertion or removal is done at the head of the list.